store a lot of water, then it takes a long time to fill it up. So think about that when you want to store energy, then it takes time. So time and energy are always going with each other. So that is the very basic concept. When we talk about energy, then we talk about time. Okay. All right, another example is that you want to store money in your pocket. And sometimes it takes a long time to store the money in your pocket. Right? And perhaps for two reasons. Your pocket is very deep, so you can store a lot of money. Another possibility is that your pocket is not very deep, but it's hard for you to get money to your pocket. But that is another concept of the storage. All right, so the time it takes to store energy into a resonator, and also the time for the energy to dissipate from the resonator is something that we should understand first. Okay, we should understand how to store the energy, electromagnetic energy into a resonator. Well, so the basic concept is that we have a structure that is in an enclosure， 它是一个被封住的范围。那 in fact 对电磁学来讲，电磁波来讲的话，其实要存一个电磁波的能量进到一个范围局限范围里头，不见得要把它们给关起来。这是电磁波里头很妙的一个观念。But we're not going to touch this in this class. But think about it, you have a storage space limited by a volume with a boundary of metal, for example, and then you want to send electromagnetic wave inside, and it cannot go out. Okay, and first you're going to establish the standing wave pattern inside. The energy will bounce back and forth, and then you can think a little bit deeper. Well, do you know why it has to be a standing wave pattern? 有没有想过为什么在一个共振的环境里头，它来回会是一个驻波的条件？ We talk about standing wave in the terminated transmission line. We talk about waveguide, wave bounce up and down, and then there will be a standing wave formed between these two boundaries. But why? 为什么？有没有想过？为什么？
因为这样的量才会就是待在原处不会传递出去。
你看哦，我若有一个，给他举例的思考的永远都是最快的。你若在这里有个球，有两面墙，拿来弹球，它能量还是在这里头。 这里头并没有要求它要怎么弹，它只要在这里头。那电磁波 electromagnetic wave between the boundary. Why is necessary that there is a standing wave inside, satisfying satisfying some boundary condition? For example, we say that the amplitude here has to be 0. Or the amplitude here has to be maximum. Why do we have such the condition? Well, this is the condition not just for electromagnetic wave, also for the string wave I show you, right? But why? Why? 为什么? Well, perhaps we'll write into a question for the final exam. But think about it, and then we can have some discussion on this Wednesday, perhaps. Why we need to have a standing wave design? But now we take it for granted that we have to standing wave into boundaries. Okay, and the wave has to follow such a rule, otherwise it cannot exist. And this is a very strong statement. OK， 没有这个条件，它不能在里头活下来。那所以活下来的意思就是说，正能量可以留在里头。OK, think about it, and we'll continue this discussion hopefully on Wednesday or in the final exam. All right. Now, in three-dimensional, you have such a few boxes. Okay. This is a rectangular box, and then you want to put energy into this system. Well, schematically, you put an antenna. Okay, you put an antenna, and then you have electric field oscillator like this. So when you have an electric field oscillator like this, matched to the standing wave pattern, then you can deposit energy into the system. Would you take this concept? Okay, Ma? Well, I always want to play some experiment for you. Think about that. This is a resonant system, right? This is a resonant system. How do I deposit energy into this tangent? 这只老鼠呢，这个被我抓了尾巴，然后呢，它跟我和平相处，还蛮愉快的。Because I talk to him， 因为我在跟他沟通，你看得出来我在跟他沟通吗？我若不跟他沟通，结果会是什么？我若不跟他沟通的话，他就不跟我玩了。So this is an obvious phenomenon. 我教小孩的时候。小时候我教女儿的时候呢，就是这个样子，然后呢，她完全不理我。后来我知道我必须要这样子教她。Okay, so I can deposit energy into this system because that I follow the phase of oscillation. I follow the phase. Well, there's a phase associated with this oscillation, and then I follow the phase. Deposit energy into this pendulum. Same thing, I need to put an antenna, follow the oscillation phase, so the energy can deposit into the system. So I hope that this is something you can catch it. So when you learn something, try to expand it to people who do not have the knowledge but have some common sense. 我说，你如果这个东西真的读懂的话，你有办法讲到那个蔡奇亚提说的人家听得懂。奎军在12月30号要去教小学4年级的学生物理，高手才有办法做得到。奎军是高手，到一个定向的学校去，然后呢，这个台大、清大、北医大学生都要一起去。Alright, so this is how we excite the energy into a field box like this. You put the antenna right at the right align with the electric field direction, and then match to the oscillation phase. Then you can deposit energy into this environment. Then once you fill up this resonator with a lot of energy, then you want to understand how long you can keep it for your application, right? So now, I want to define some parameter to describe how good an oscillator can store energy. All right, we call this quality factor Q. Quality factor Q. Well, we want to understand how long the energy can be stored inside the cavity. Then we want to understand how the energy is going to dissipate it from the system. Okay. For this cup, I store water inside, and the loss of the water is going to be associated with the leakage of the water going out, or for some reason that this water could be absorbed by the boundary, for example. For the electromagnetic wave, when you look at this, well, there's for example, strong surface current on the surface. Then this is going to introduce Ohmic loss. Okay, and this Ohmic loss is going to dissipate the energy inside. So let's define the energy stored inside versus the dissipation of the energy per unit time as a ratio called quality factor. If this quality factor is big, this means that you can, on average, you can store a lot of energy inside. At the same time, the dissipation of the energy is going to be very small. And we call this, hey, this resonator have a good quality. We call this quality factor, okay, quality factor Q. But there's a subtle physics associated with this quality. Okay, we're going to figure out how this Q value will define the bandwidth of the system. Okay, well, what do you mean by bandwidth of the system? Then let me go to this mouse again. Well, I say that I need to follow the phase to store energy into this pendulum system. So this is the system. Well, in the old time, perhaps if you go to some antique museum, you can still see some pendulum the clock. 你有没有看过这个 pendulum clock？ 大概只有在博物馆里头会看得到。哇 ，pendulum clock 就是这个东西上头画了一个这个机械的齿轮，然后它震动的话呢，事实上是有一个固定频率。Okay, there's a fixed frequency associated with it. So you can use this to count the count time. Okay, so this means that there's a certain frequency associated with this rhythm system. When I say I follow the phase to store energy into this system, in other words, I'm also defining the frequency of my energy deposited into this system. So this is the narrowband system. Okay, a rhythm system usually is a narrowband system. Only certain frequency will be accepted by this system. If I do this, it's not going to deposit energy into the system. Okay, and if I do randomly the excitation, it's not going to accept it either. So this means that I need to follow the frequency. I need to set the frequency of my hand to be the same as this one, and also follow the phase so that the energy can be deposited into the system. So think about that if I have a resonator like this. If I have a resonator like this, this means that there are only certain frequencies this system can accept the energy. Okay, and cavity Q in fact is relevant to this. So I hope you see the experiment and catch the basic concept. Okay, all right. So cavity Q tells you how good you can store energy, and then we're going to relate this cavity Q to some bandwidth of the system. But mathematically, let's write down. This is the average energy you deposit into the system. Okay, and you have a power loss. But we take the power loss to be in one cycle of oscillation, so that when you divide this Q, you get a dimensionless quality. 所以你能量除以能量，你就没有一个单位在那个地方，只是一个数字。这个数字告诉你说，哇，我这个 cavity 能够多么好的这个储存这个能量。Alright， 经验 ，understand this, right? You got a concept. You like my experiment? 你喜欢我刚做的实验吗？还好来，任何这个问题也可以拿来摇一摇，你会发现呢，事实上你要让它摇起来，不是用蛮力就可以的。Okay, good. So we have a definition, and then we end up having this expression. So this is reasonable to you. All right. So now we need to connect the formula to electromagnetic energy. Long time ago, you knew that there's electric energy and magnetic energy associated with electromagnetic field. Okay, and this is the expression you learned it a long time ago already from the electrostatics, magnetostatics, and then pointing vector. We all have seen this, but don't forget that when you do an average calculation using complex notation for time harmonic field, don't forget that you have 1/2 in front of it. But the good thing about the electromagnetic wave is that you knew that in a wave, electric field and magnetic field are coupled together. Okay, so in fact, when you do the calculation for WD and then WH, you notice E and H are coupled together in an electromagnetic wave. So in fact, these two terms usually are equal to each other. So if you want to cross these two together, usually just one term. Okay, either this one or this one, and multiply with factor 2. But when you do the average calculation, you have a factor 1/2 here. This 2 usually will just cancel with this 1/2. Okay, so in fact, you just calculate one term, then that is going to be your answer. Right, so this is shortcut for you to do the calculation. Now, we know how to calculate this, the average stored energy. Then we need to know the primary loss. Well, if I want to calculate the loss of my water in my cup, then I need to calculate how much I drink it, right? Or how much it's going to leak out. But for electromagnetic wave, the primary loss, if you don't have any, if you don't have any open aperture in the boundary, the primary loss is going to be the ohmic loss. Okay, so for this term, it's going to be ohmic loss. But occasionally, for some applications, you open the hole here, then you have additional loss. So be careful about that. Okay. Right now, think about this: the bucket of the water. You, for example, you open the hole here and then pour water into this system. Okay, think about you have. If you want to fill up the cup, you drill a hole here, and then from outside you pour a lot of water into this cup, and then it takes some time to fill it up. Okay, so you can imagine that, right? Now, once this is filled with water, and I start to remember there's a hole here, and I start to do this. It's going to come out. Water is going to come out, right? But I have a very good cup, but it's still coming out. It takes some time for the water to come out. And in fact, this is just the symmetric process. Filling up the cup with water through a leakage hole here basically is the same as the pouring water out from this leakage aperture. This is a symmetric problem. Okay, so the time it takes to fill up this cup will be symmetric to be the same as the time to leak out the water from this cup. This is a symmetric problem. Imagine that you sort of having a small aperture here, and then you have a constant flux of the water coming in, and the rate of entering this cup is limited by the aperture. Okay. Same thing if you try to leak the water out, the rate of leaking is also limited by the same aperture. So this is symmetric problem. So from this, we can calculate the filling time and decay time of an oscillator. They are just the same. Another example is that you have a battery. Okay, you have a battery, and then you try to fill up a capacitor, and there's a time constant associated with this filling process. Right, this is equal to RC. Well, then you create another symmetric problem. Once this is filled up, and then you have a switch here, then you cross this, then you start to have discharge of this capacitor. The decay time is still the same. Okay, so this is a symmetric problem. Similarly, for resonator, you have a decay time that is the same as your filling time. It's just like a capacitor or just like an inductor. It's a symmetric problem. the time for filling up the energy is the same as the time for dissipating the energy for RC circuit or RL circuit. Okay. So the decay time it's easy to see that the decay time will have a characteristic value tau going down like this, and this is going to be a long tail. So under such a situation, we define the decay time that is equal to the stored energy going down to about 37%. The time it takes for the stored energy to drop to the 37% of the original value. 所以这是我们定义这个它的 decay time 或 filling up time 的一个方法。Okay. But Fourier transform, Fourier analysis tells you that with a finite width of the energy decay is associated with frequency bandwidth given by this very simple expression. But I have an approximation here. This is just approximately correct, depending on the profile of this decay. Okay, but usually this is roughly correct. The time and bandwidth product is going to give you a constant, and this defines the frequency bandwidth that you can deposit energy into the system. Okay, this is going to tell you, for example, if you want to excite this pendulum, the excitation frequency, my excitation frequency has to be matched into such a width. That is about 1 over decay time. Okay, by virtue of the Fourier analysis. Now Fourier analysis is a very powerful concept. Okay, it is the sort of basic thing for all the linear systems. All right. So now we try to connect the capital Q to this decay time, and then try to connect the Q to the bandwidth of the resonator. Okay. Now let's do a simple calculation. Okay. Based on the energy conservation, we knew that the decay of the energy goes to some dissipation. That is related to the power loss inside the cavity or leaking out of the cavity. Okay. So if you do a time derivative to the stored energy, you understand how much the power is going to dissipate in the cavity or going away from the cavity. And this is the roughly equal to the stored energy divided by the decay time. Okay. So if we go through this calculation, then we have a definition of Q relevant to this average stored energy and the power loss, right? So we can quickly write down the relationship between tau and Q, because Q was previously defined like this. Depends on the average energy stored inside and also the power loss per cycle. And this is the frequency of the oscillation. Okay. So now you relate the tau to Q, but then this tau is related to the bandwidth, so you end up having this expression. Very nice, the simple expression. It tells you that, well, if you have the ability to store a lot of energy into a resonator, then the bandwidth can be very small. What does it mean? You have to control your hand very well to match to the oscillation of this resonant system. Otherwise, you cannot deposit energy into this resonant system. Okay. So think about this experiment, and then you understand that how well you have to control your hand to deposit energy into this pendulum system. Okay. 所以呢，你将来如果设计一个high Q 的电路， well, for example, your cell phone is quite small, but it's very sensitive to the receiving of the electromagnetic wave, right? And that means that there's a very high Q resonator. There's a very high Q circuit in your cell phone, so that you can accumulate the signal to be high enough so that you can talk. then the frequency has to be very precise to match to the resonance circuit, the high Q circuit in your cell phone. Otherwise, you are not going to pick up the signal. 你可以想见这个想法吗？ Because next time we'll be talking about antenna, receiving antenna and transmitting antenna. Okay, but when we talk about cavity Q, when you can, okay, let me go back to this. When we talk about this cavity Q, this means that we sort of try to quantitatively to describe how good this cavity is for storing energy into it, right? But why do we want to store energy into it? Well, 想想看, think about you have a circuit inside. You have your receiving circuit inside. If you can store energy into this, for example, this is connected to another antenna outside, and then you can deposit energy into this system. What happens is that the stored energy will become larger and larger. So it's very easy that you put a sensor, you put a circuit here to pick up the signal. 如果说我没有一个high Q 的一个 circuit 在那里的话，我直接把这个接到我一个电路上头来，抓这个讯号可能太弱了，因为电磁波就跑得到处都是。但是呢 ，if you have such an energy storage device in your circuit, then the amplitude, the field amplitude can become larger and larger, become very big, right? So if I put a circuit here, it will be very easy to detect it. So usually, if you have an antenna, then you connect it to an oscillator circuit to store energy. And then once the amplitude is large enough, then I can detect it. That's how you design your circuit. Okay. On the other hand, if you have a very strong electromagnetic wave coming in, then you store energy into the oscillator circuit. You could damage the oscillator circuit, okay? Because the field can be very, very strong if you store energy into the oscillator circuit. And this is how people develop microwave weapon, 就是微波武器。一堆这个无人机过来的时候，你如何把它这个整批把给拉下来？你就是把它频率弄对之后呢，让它自己的共振的这个电路能爆掉。OK， 那就是微波武器。OK， 那所以呢，这里头就牵涉到就是how good you can store energy into the resonator, determined by this Q factor. But even if you have very high Q factor, and then you want to damage it, the drone, 你如果要做一个微波武器的话，你的频率要对，不然的话这个能量灌不进去。Okay, so this is the basic concept and very realistic. Okay, when you design your circuit. All right, so this is pretty much the basic concept of the resonator I will review. 有时候我觉得我上课的时候呢，最精彩的就是第一节，然后第一节上完之后，你可以开始睡觉。因为第一个 section 的话，就是基本概念就告诉你，其他的再下来就是一堆的计算。那你只要有耐心的话呢，就可以把它完成。OK， 第一节的部分有没有问题？这样。把这个基本观念带走，你就很容易这个往下。Alright, now we want to look how we specifically write down the field expressions associated with an electromagnetic resonator. Okay. Well, basically we try to create more boundaries to confine the energy. But think about we have the definition of TEM, TM wave, and so on. And in the hollow waveguide, we do not have TEM mode. Okay, so but the definition of the TEM mode becomes quite convenient when we discuss the physics, because we can sort of categorize the modes inside the waveguide. But now we run into a problem. When we define T, for example, Tn mole, we define that there's an electric field along some axis. Well, along some axis, in fact, is going to put a bottleneck to this topic, because now, how do you define a reference axis? Well, same thing when I talk about T mole, we have the magnetic field along z direction. But for an electromagnetic resonator, we don't have any specific axis that could be more important than all the others. Well, we define z-axis because we have a energy propagation in mind. We want to propagate energy along z direction. So this z-axis is more important than x and y. But for an oscillator like this, can you claim for an oscillator like this, 你有没有办法说，哎 ，z 比 x 还重要 ，z 比 y 还重要？除非你把这个应用讲清楚，否则的话呢，事实上 x 也很重要 ，y 也很重要，这是同样的这个地位 ，OK。那但是呢，你如果失去TETM 的这个 reference 来讨论这个题目的话呢，就变得很困难，因为你会把所有的 mole 都混为一谈。所以呢 ，TETM 等等的这个定义，是因为你有一个 reference axis 在那里，一个重要的 reference axis 在那里，所以呢，你可以用 TETM 的讨论。那resonator 呢，留意到就是将来你在定义 Z 的时候呢，要跟你的应用做一起考量。那为了方便讨论，我们还是选择 Z 的方向呢，是一个重要的方向。But this z direction can be redefined anytime. Okay? For example, if I say that in a resonator we have a TE mole like this and like that. In fact, if you choose the reference axis differently, then TE mole could become TM mole. Be careful about that. Okay? For now, we'll still choose z direction as an important reference, and then define TE and TM mole. All right. So let's just continue the discussion from the waveguide. For waveguide, you have important axis along z direction, and then you have energy propagating along this direction, and cross-sectional area like this. So this is the dominant Tm mole in the waveguide. The straightforward extension of the waveguide to a resonator is that you put a boundary, just block the z direction, and then you confine your energy inside like this. And of course, once you add boundaries, then you need to satisfy the boundary condition, okay? And you will be expecting some standing wave going along this direction. But this is a Tm mole for you will be expecting an electric field along this direction. So when an electric field going to the normal of metallic boundary, it's going to have the maximum value. So you'll be expecting the field dependence, EZ, the field dependence is going to have a cosine dependence along this direction. Okay. So let's write down the expression. We convert a waveguide into a resonator. We'll be writing down previously the dependence along x and y direction. We had this solution before. And then along this direction, you're going to have a wave going back and forth like this. So you have two terms, two propagation terms. OK， 这个是我教书很多年之后呢，觉得这是最好的讨价包，也就是最快的方式。你不要去算一大堆的这个mass equation 啊，或者是Hamilton equation， 你就直接把这两个方向的场把它加起来，然后你告诉你自己说。嘿，这个是之前的这个dispersion relationship. But now along z direction, you have additional 之前就有一个 propagation constant 在这个地方 ，right？ 这之前的这个dispersion relationship, you already knew it. So we did not modify anything. This was the one you had before, right? For the waveguide. So nothing has been changed. Except that we need to specify the boundary condition here. Well, so one possibility is that this is plus, this is minus. and you know that you have two waves, counter propagating inside, then it's a choice for the plus sign or minus sign based on the boundary conditions. Well, if I have maximum value here for the normal component of the electric field, then I want to write this into a cosine dependence. Okay, because I want to maximize the field, the normal component of the electric field on these two boundaries. So of course, I'm going to introduce this cosine dependence here. This is beta value, okay, and you will have maximum value here for EZ and maximum value here for EZ. So now you know that you have an eigenvalue. The beta value has to be like this, so that right at z equal to 0 and z equal to d, you have maximum value. 所以这个等于是完全用物理的直觉就把这个答案猜出来。OK, z component electric field。所以这个过程的话，是对你来说是不是够直接？make sense to you, right? 你把这个边界放上去之后，这里波就在这里震荡，然后它必须出波，然后呢 z 的 component 是 normal component，you maximize it, so you choose this cosine solution. That's it. So then you don't need to go through a lot of tedious calculations. And previously you have this dispersion relationship, so just replace this with p pi over d squared. Then you have the resonance frequency. Alright, just replace this with p pi over d, and then you have resonance frequencies based on this expression. So this is very straightforward, much easier than the direct waveguide or Bessel function kind of calculations. Okay, and it tells you that the frequency inside is going to be discrete. Okay, the frequency inside is going to be discrete based on this m and pi, m and p combinations. And previously for the t m mole, you cannot have 0 for n or n. 这个任何一个这个 mn 都不能等于0，等于0的话呢，你的 Tm mole 的讨论就没有意义了。所以呢，但是呢，你所以这里是 1 1， 但是对这个 p 来讲的话，它可以是0，不会把这个 Tm mole 杀掉。所以呢，你会有一个 Tm110是它的 dominant mole 的一个结果。Okay, so this is the sort of quite okay, right? 经过这个 Bessel function 跟 direct waveguide 之后，现在相关的东西就开始简单了。Alright, Moore field basically the same as the Tm11 Moore field, except that at the z boundary you need to make sure that the field boundary conditions are satisfied. Okay. 所以呢，我们来看一下，这个比如说在 z 的这边界上头的话，那我们有几个 guideline， 也就是说，the initial component of electric field has to go to 0, so the electric field along this direction has to go into the normal direction of the surface. Right? 同样的，我们来看一下这个 ex 的话呢，在 x 的面上头，因为 ex 的话是朝着 x 的方向的这个电场。那你的一级在这个面上，真正面上呢，你的电场强度会最大，对一个金属的边界来讲，所以你会有一个 cosine dependence. But then for Ex along this direction, on the y and z surface, this direction is the tangential components. So you have sine dependence for the y and z surface. OK, 所以当你写下这一场的时候呢，每一个都有它的道理在那个地方，不管是electric field或magnetic field. So once you have the z component of the electric field, you can solve all the electromagnetic field in the cavity. So then be careful that, for example, for x components, then along the x surface that is the normal component. Normal component of the magnetic field on a surface is going to be equal to 0 because there's no chance to induce surface current. But S component of the magnetic field is going to be a tangential components along y and z direction. So you maximize the value because the surface current is introduced. So you have cosine dependence. OK， 然后在这里头，这个比如说 E 跟 H 之间，它之间的相位差是多少？差90度，代表什么？这都是 standing wave 的 pattern， 所以呢 standing wave does not carry average power, so the pointing vector will go to 0 along any direction. So you see that for any electric field and magnetic field, there's a 90-degree phase difference between electric field and magnetic field. Okay, so that the average pointing vector gives you 0 average power because the standing wave inside. Right. 所以这些都基本的概念，你可以应用这个基本概念，你可以把它的field dependence sin 或 cosine 全部都写出来。只是 prefactor 的话呢不容易记 ，OK， 但是它的 sin cosine dependence 呢是清楚的。Okay, so this is the Tn rectangular resonator, and the next topic is going to be the Te rectangular resonator, and again, we're going to define an important direction along z direction. Then we can categorize the mole having magnetic field along z to be a Tm mole inside. Well, the process, the steps are basically the same. You pick up the dominant Te mole from waveguide, and then cross down the boundary along z direction. Okay. And you try to satisfy the boundary conditions when you write down the field expression. So let's write down the field expression. Again, you establish a standing wave along z direction, but you do not know the sign of this those terms. But you know that this is the along z direction. Z direction is normal component of the magnetic field on the metallic boundary. So it has to go to 0. Okay. The tangential component of the magnetic field will go to maximum value on the surface because there's a surface current induced on the metal. But if you have a normal component of the magnetic field on a metallic surface, then the value has to go to 0. So you choose a sign solution. Okay, you choose a sign solution for this. So to take out the tangential component of the magnetic field on the conducting surface. 所以这个计算变得其实很简单。你若经由课本的那些这个教科书的计算的话呢，你会丢到 Helmholtz equation 里头去 match boundary condition 等等的话，到这出来结果还是一样。Alright, so you choose the eigenvalue along z direction to be p pi over d, except that you have a sign dependence. But previously, when you write down the Helmholtz equation, you have such a dispersion relationship. Well, along z direction, you have a propagation constant, but now your propagation constant is a discrete value defined by the boundary, that is p pi over d. So quickly, you can write down just substitute this p pi over d into this dispersion relationship, then you can write down the same resonant frequencies defined by those discrete numbers m and p. Well, 在这里呢，你这里不能变成0了，变成0之后呢，你的 z component h field 就是等于0，不再是一个 T 目，所以这个最小值会是1。Okay. Previously, you have dominant 1,0 mole, and the third index, the minimum value for the third index is 1, so you have the dominant mole will be 101. 但是这里呢，是我们之所以把它写成 dominant mole Te10，是因为 A 比 B 还大。 OK，A 比 B 还大，所以我这里呢是1。如果 A 比 B 还小的话，我的 dominant mode 会是 TE01。So be careful about that. Okay. So you have the same expression for the resonant frequencies of TE and TM mode. Then let's ask one question. What is the dominant mode inside such a box? Okay. You have the same expressions. And but there are certain conditions for the M and P and so on. But before we do that, let's take a look at to determine the dominant mode, we only choose the smallest value of this one. Okay. But then this box can support TE and TM mode, so we need to consider TE and TM at the same time. Before we do that, let's just write down all the field components, because once you have the Z component of the magnetic field, you can have all the fields for the other fields. So just do the calculation, and again, I draw your attention on those characteristic sign and cosine dependence based on the boundary conditions. Okay. 所以写出这些不困难，你说边际条件概念很清楚的话，这个前面的 prefactor 比较困难一点。但是你如果要去画它的 field pattern 的话呢， you just need to know the sign cosine dependence. Okay. 所以这是写出来的结果是这个样子。Alright, let me take a break for 10 minutes so that you can relax a little bit, and we'll come back in 10 minutes.